Bismillahirrahmanirrahim. Assalamualaikum everyone. My name is Izz Hakim. I'll be presenting my technical paper review titled Deep Moveout for Seismic Data Processing QCB4213. Our lecturer is Dr. Abdul Halim bin Abdul Latif. First of all, we will go through the introduction of Deep Moveout. The definition of Deep Moveout in textbook with the title of Applied Geophysics that is written by Telford in the year of 1976. It is defined that the original classic definition has to do with the effect of dip on the timing of events on chart records. However, in the year of 1987, Dragowski has defined dip move out as a migration process which transforms the pre-stack dataset so that each common midpoint gather of traces actually contains events from the same depth point. In simpler definition, DMO is correlated with NMO, which is normal move out, but with reflector of a dipping angle. Next, we will go through the problem statement of the presentation. There are many ways in conducting the dip move out analysis to provide the best product of seismic processing in the industry of oil exploration. Therefore, the understanding of the evolution of dip move out analysis is crucial in order to obtain the best processing results. Several DMO algorithms that includes pre-stack partial migration, Fourier domain DMO, and offset continuation is considered commonly used to conduct DMO analysis. Thus, to understand the use of each algorithm is important since each algorithm has its own strength at different case studies. For the objectives, there are several objectives for this presentation, where it is to compare the DMO algorithms within recent and past methods, to understand the concept, definition, and method of DMO, to conduct research studies regarding DMO and identify the gaps in research, and lastly to identify the available methods that can be used to conduct DMO analysis. Before we move any further, let us look at the difference between NMO versus DMO, where NMO is the normal move out while DMO is the deep move out. Normal move out is defined as the effect of change in travel time t of wave reflecting on a flat surface reflector when the offset distance between seismic source and geophone is changed, while deep move out is defined as the difference in the arrival times or travel times of a reflected wave measured by the receivers at two different offset locations that is produced by a reflector surface that has a dipping angle. Do note that the concept between both effects is actually the same. However, the surface reflector characteristic that make them different, where NMO is reflected by a flat surface with no dipping angle, while DMO is reflected by a dipping surface reflector that has angle of dip. Let's continue with the history of dip move out. The former algorithm is known as devilish, that as stated by Judson et al. In 1978. The devilish is meant by dipping event velocity inequality leaked by Sherwood. Unfortunately, because of certain numerical approximations, the performance of original devilish was inadequate and the process gave up for quite small dips and offsets. Later on in 1980, Yilmaz and Klebold worked on another downward continuation technique which they termed partial pre-stack migration. Later on in 1981, Dragowski and Rocca which described the time domain impulse response of the DMO operator together with its Fourier transforms. In 1982, Bolondi et al. Subsequently provide an alternative finite difference approach that is termed offset continuation. A Fourier transform implementation was taken up by Hale at Stanford University that is also termed the algorithm deep move out or DMO. And then Dragowski in 1985 described an integral or Kirchhoff-style implementation based directly on the time domain impulse response described in the early paper by Dragowski and Rocca in 1981. Moving on with the purpose of deep move out, it is used to migrate each trace to zero offset so that each common offset section becomes identical to a zero offset section. Next, to interpolate dead traces, according to local time dips without those dips having to be estimated by a separate operation. Next, to remove steep, deep coherent noise without the artificial alignments that associates with deep filters. Next, to improve signal to noise ratio. Next, to improve velocity analysis and provide velocity that is appropriate for migration as well as stacking. Next, to preserve diffractions through the stacking process as to give improved definition of discontinuities after post-migration. And lastly, to provide cheaper alternatives to make post-stack time migration equivalent to pre-stack time migration. Moving on with the traditional method for dipping reflector analysis. During those days, most of the methods utilize common depth point or CDP trace sets either through summation or correlation between coherent reflection events into time velocity domain. The output represents the reflection amplitude, power, or coherence versus time domain. Manual interpretation were used to interpret the maps. Velocity function is constructed by connecting the peaks in time velocity domain that is representing the primary reflection energy build-ups. During those days, the operation is more to manual derived. However, during recent time or conventional method of deep move out, the DMO can be performed in a number of ways with the help of different algorithms that were derived based on different situations. However, note that different algorithms are highly possible to give different results even though the same dataset is used. This is due to the factors that is being taken into account in each of the algorithms is different with their own ways. Several algorithms that are usually used to compute deep move out are pre-stack partial migration, Fourier domain implementation, and offset continuation. Let us first start with the pre-stack partial migration. The theory of pre-stack partial migration is closely related to the problem of seismic imaging. The reflectivity at any x and z is then seen in the limit of zero travel time and zero offset. The mathematical description of such an imaging process is given by the double square root equation. Conventional processing can be understood as an approximation to DSR, or also known as double square root. Imposing the zero dip and zero offset assumptions, we separate the double square root operator into two terms. That is, involving the zero dip move out correction applied in offset space and involving the migration of zero offset section applied in midpoint space. Wide variety model experiments and field data has improved by incorporating this procedure. The mute zone during stack is considerably reduced. A better imaging is achieved by migration after stack, and dipping events can be delineated much more successfully. There are several disadvantages for pre-stack partial migration, which it consists of unfamiliar term that is a function of offset, dip, lateral velocity gradient. It is also best to be used only if statics problem where the near surface lateral velocity gradient is often significant. The double square root equation is given as shown in the screen, where y is meant by the midpoint value and h is the half offset value. Moving on with the second method, where the deep move out equation is implemented by Fourier transform equation. Deep move out by Fourier transform is a method of performing deep move out correction in the frequency wave number domain. The implementation of this method, which resembles the implementation of a discrete Fourier transform, is quite different from compares favorably with previously published finite difference DMO algorithms. This DMO method is to be used for a high complexity slopes, since general equation of deep move out could not be used and has high uncertainty when it comes to multiple or complex slopes. The general deep move out is defined by as the equation shown in the screen, where it consists of simple trigonometric identities and some algebraic manipulation, then yield the following expression for the travel time t in terms of the source receiver midpoint y and half offset h. The Fourier transform are then expressed in terms of NMO corrected data by using following changes of integration variable as shown in the screen. And then an integration is applied to the equation, where finally the inverse Fourier transform is applied to the reflector to obtain the desired zero offset sections, where the final equation will be as shown in the third equation. The processing sequence of applying DMO by Fourier domain is shown here, where a synthetic constant offset section consisting of 8 impulses is obtained, and then after applying NMO with velocity of v equals to 2 km per second, for example, it will be showing as shown in the B figure. Then, after applying velocity independent deep move out using Fourier DMO equation, the figure in C will be the result. And lastly, in the D figure, it is the result after migrating with velocity equals to 2 km per second. Moving on with the next method of DMO, which is deep move out by offset continuation. This method is developed by Bolondi in the year of 1982. The transformation of common offset to zero offset sections is usually carried out via the normal move-out correction stated by Sharif 1976. This correction is fully valid in the case of horizontally stratified layers only, when the dips are in conflict, however, which is always the case when the reflectors are broken or discontinuous. There is no NMO correction that makes possible the stack while preserving full horizontal resolution. As an example of a case study where a small hyperbolic ellipse is obtained, the equation of curve pertains to the velocity-independent ellipse described by the equation as shown in the screen of equation 1. By the curve extends laterally up to the point where the slope of the ellipse equals to 2 over v, where v is the velocity of the medium, the operator will then be as shown in equation 2. This has shown that in order to deduce the zero offset section from the non-zero offset one, it is necessary to carry out not only the NMO correction but also the convolution with the time-varying space stationary operator whose impulse response clashes in the high frequency limit with the smile. Henceforth, this convolution operation is called offset continuation. It is also known as a simpler operator since the equation is not as long as the other two methods. In conclusion, there are improvements in the industry of seismic processing industry where geophysicists are putting their full effort to solve and come up with the best solution for every challenges that has been faced by former geophysicists. Thus, to produce the best solution with the least uncertainties, since all exploration is very cost consuming and eliminating each uncertainties is the job of geophysicists to avoid failure in exploration due to misleading information in seismic data. As for recommendations, there are many other ways in computing the DMO of a seismic shot gathers. Therefore, as a geophysicist that is given the responsibilities for seismic processing, it is crucial to understand all of the available algorithms in order to provide the best solution at every real world case scenario. Which one is best and which one is better? That's all from me. Thank you.